solids. The general properties of solids reflect the orderly arrangement of their particles and the fixed locations of their particles. In most solids, the atoms, ions, or molecules are actually packed tightly together. As seen here, this is a picture of sodium chloride, okay? Where the green ones are the chlorides and the blue ones are the sodiums, and they fit in that way. So in most solids, the atoms, ions, or molecules are packed tightly close together, and they're dense and not easily compressed. They are kind of as tight as they possibly be. So they don't flow because the particles in solids tend to vibrate about in fixed points. And that's something that it's a true or false number 1 on the assignment. Does everything move or does everything vibrate? Yes, everything does. It's just how tightly packed together are they will tell you if it's moving around the room, if it's moving like within your water bottle, or if it's just sitting there and you can't tell that it's moving. Okay? So solids do vibrate in place. They just don't move for us to see. So melting and freezing is when we're going between a solid and a liquid. We kind of all know about this all the time, right? So, or you've heard about this before. So when you heat a solid, its particles vibrate more, so because it's gaining energy, kinetic energy. And it will reach a point when it's vibrating so much that the particle will actually break itself down, and that's when the solid melts. So the melting point is the temperature at which the solid changes, which the freezing point is the same exact temperature as the melting point. Okay? Sometimes people don't realize that. But the temperature, like if it's like how we had the equilibrium arrow before. It doesn't matter which way you're going. It's going to be the same temperature when it makes that transition from one to the other. Okay? So the melting and freezing points are the same temperature. So if we draw another equation, is it okay if I move on? Okay, so let's draw our next equation. So if we're going from a liquid to a solid, draw your equilibrium arrow. It doesn't really matter which the top one points to and which one the bottom one points to. But when you're going from a liquid to a solid, we call that what? What's it called when you go from a liquid to a solid? Freezing. Yep. No matter if it's water or if it's something else, we literally call it freezing when you go from a liquid to a solid. And then a solid to a liquid would be the melting. Okay, so like we've done things in lab before where we have actually melted and refroze chemical compounds that are not water. Like we did one at the beginning of the year and everybody's like, oh, it looks like ice, it looks like ice. Well, really all we did was we heated it up so it went from a solid to a liquid by melting it. And then after we let it cool for a little bit at room temperature, then it froze back to being in a solid. It just looked cooler because it had melted before. So it just melted and refroze in a different form. Okay, so that's something we've heard of before, right? Okay, ionic solids have high melting points because they're relatively strong forces that hold them together. So sodium chloride, for example, has a melting point of 801 degrees Celsius. That's 700 degrees higher than water. No wonder it's usually a solid. Molecular solids have relatively low melting points, which is why they're not usually in solid form when we see them. We usually see them as gases instead. So not all solids melt. Wood and cane sugar actually decompose when heated instead of actually melting. And that's because if we were actually wanting to melt them, we'd have to have it at a certain specific temperature and pressure. And normally we don't do that. Like when you're having a campfire, it's just whatever the pressure is outside that day. Okay? Alright, this is what I've taken out. Because the reason why I took this out is because actually on the AP exam, like for if you take AP chemistry and like all the standards that go along with that, you don't actually have to know anything about unit crystals. So I'm taking it out so we don't have to talk about it now because you don't have to know about it later. Okay? But most solids are crystalline in form. And crystalline means that the particles are arranged in an orderly, repeating, three-dimensional pattern that we call a crystal lattice. Okay? So this is an example of a crystal lattice here. There are actually different types of crystal lattices, but that's unnecessary information for us in this class. Maybe when you're like in your 3rd or 4th year chemistry in college, then you would actually get into that if you needed to. So the shape of a crystal reflects the arrangement of the solids within the particles within the solid. So like you can actually grow crystals, and you could see this orderly pattern. We did not grow crystals this year because we did not make the borax ornaments. So we might have to grow a crystal. We'll see. That might be something good to do on Thursday, Friday. Okay, I'll think about it.
Let's do it Friday for sure while we
Well, it has to do with
Is that when
the plan for the project.
Oh.
So it's okay. So crystal systems happen when we have these crystalline structures, right? The crystal has sides or faces, and the angles at which the faces of the crystal intersect are always the same for a given substance. And that's why a crystal, like especially an ionic crystal, will just form on top of each other and get bigger and bigger and bigger, okay? So the shape of the crystal depends on the arrangements of the particles within it. Like a diamond, I showed you guys the shapes before of diamond, right? Like the diamond versus the graphite? No? Okay, well I'm going to have to do that this chapter. Okay, the smallest group of crystals, particles within a crystal are called the unit cell. Okay. Allotropes are substances that have two or more different molecular forms. Carbon is an allotrope with diamond and graphite. These are the shapes that I have that I'm going to pull out to show you. There's also something called the Buckminster fullerene buckyball, buckyball for short. It's a super humongous complex crystal, and one unit of it is like 60 carbons connected together in like a soccer ball kind of shape. I have never made one, so I don't have a model of that, but maybe if one of you guys wants to try and do that, I'll give you a couple more looks. But, so, like diamond, okay, so diamond is up here. We all know diamonds are pretty tough, pretty hard, right? It's kind of hard to cut. You can't cut through an actual carbon atom, so it's important to know that. Then graphite is like what's in your pencil right now. Graphite, there are sheets of carbons that are connected together, stacked on top of each other. And then in order to write on your paper, what you're doing is there are intermolecular forces, or there's different forces that are holding the sheets together. And as you apply pressure on your paper as you're writing, the pressure from your writing will break the forces that are holding the sheets together. So the writing on your paper is actually just the leftover sheets after they've been broken off. Okay? The buckyball looks like a soccer ball, like that. And then this is called a nanotube over here in the bottom right. And it's a structure of carbons in hexagonal form that it's just like a tube of all these. So there's empty space in the middle. So the carbon has a lot of different allotropes. I mentioned the first three, but there are more than just that. So allotropes, many different ways to arrange the same thing. Okay. Non-crystalline solids are usually called amorphous solids. So it lacks an ordered internal structure. A glass is the most common thing or example of an amorphous solid, because a glass is a transparent fusion product of inorganic substances that have cooled to a rigid state without crystallizing. So, like you heat it up and then it cools quickly, and so that's what makes an amorphous solid. So, besides glass, we could also have rubber or plastic or asphalt as well. Okay, I would write down two. Don't write down all three. So glasses, when they're cooled too fast like that, they're sometimes called supercooled liquids because they're so super cool, right? So supercooled liquids are glasses. The names of moving back and forth between solid and gas, which we haven't talked about yet. The first is sublimation. The change of a substance from a solid to a gas without passing through the liquid state is called sublimation. Sublimation occurs in solids with vapor pressures that exceed atmospheric pressure at or near room temperature. This doesn't happen very often. Sublimation, turning from a solid to a vapor. The most common form that you might ever see. Who knows what dry ice is made out of? What? Not liquid nitrogen. Carbon dioxide is what it's made out of. Dry ice is carbon dioxide. I didn't get any dry ice this year either. Maybe I need to get some.
How do we make it?
You can't make it. I just buy it from here. Because you have to condense it at its really extreme high pressure to do it.
How do I do that?
I don't have the equipment for that. I don't know. But anyway, guys, we are almost done with this. It's really hard for you guys to pay attention today. So, dry ice, when I put it on the table, and it starts like foaming or like it starts like billowing up, right? What's it doing? When you just let it sit out at room temperature, what's it doing? It's turning into a gas, right? So it's not called evaporating because it's not going from a liquid to a gas. It's going from a solid to a gas, and so that would be sublimation. Okay? So the way that I remember sublimation is sublimation starts with an S, and so it starts in the solid form and then goes to a gas. Okay? So dry ice is a big example, or ice melting on a sunny day, you might not see it turn into a liquid, so that's another example. So just write down dry ice and you'll be done. At a very extreme pressure it would, yeah. But not anything that I can make in this room, so. The backwards way, so if you go from a gas straight to a solid, is called deposition or deposition, however you want to say it. I know it's a weird word, okay? But it deposits into a solid form throughout. Did everybody write that down? Do you have to write anything down? Okay, so let's just fill this in really quickly. Please, whenever you see this, always make sure you identify where the solid, the liquid, and the gas circles are, okay? And also which direction the lines are facing, the arrows are facing. So, from a liquid to a solid, what do we call that? What's it called when you change from a liquid to a solid? It's freezing. Yep. What about the opposite way, solid to a liquid? That would be melting. Okay. Then from a liquid to a gas, what do we call that? Evaporation or vaporization. Either is fine. And then if you're going from a gas to a liquid, that's called condensation. Okay. Then the last two. When you start as a solid and you go to a gas, that's called sublimation, because it starts with an S. And then the opposite way, from a gas back to a solid, deposition, deposition, however you want to say it. Okay. The reason why you have to pay special attention to that is because people write this down wrong in their notes the first time, and then they go and they get it wrong like every other time you have to write it down. So, just make sure you wrote them down correctly. Okay? One more thing, and then we're done. Okay? I'm ready to erase. So, a phase diagram is the last thing we have. And this is where things get really tricky, okay? And this is where you come into play where maybe normally it doesn't go from a solid to a gas, but maybe we could get it to be like a solid to a gas. So, the relationship among solid, liquid, or gas phases is shown in a phase diagram. A phase diagram gives the conditions of temperature and pressure at which the solid, liquid, or gas is existing. When you're looking at a graph, which I know we have a graph on ours that's a little bit different, but the x-axis is always temperature, the y-axis is always pressure, and then it's like it has like a little Y shape on there, okay? The lines are telling you that changing over period. So like the line between the solid and liquid section is telling us that at that temperature and that pressure is when it's going to be changing from a solid to a liquid, or vice versa if you go the other way, okay? So there's a lot of information shown on these, but let's just label ours. The condition of pressure and temperature which the two phases exist of equilibrium indicate on the phase diagram by the line separating. So here this is for water, okay? But it's showing us ice would be the solid form, water would be the liquid form, and then the vapor would be the gas form. So whenever you're labeling this, the left is always solid, the middle is always liquid, and then the right is always the gas. Because at a higher temperature, it's going to move a lot more, so it's going to be in the gas form. I know that that's not the one you have. we're gonna just keep going. I'm almost done. So the triple point is something that's super important on here. So I think this is the one that looks like your notes, right?
Yeah.
Where solid, liquid, gas. The triple point is the point at which all three phases are in equilibrium at each other. So you can actually have all three existing at the same time. So the triple point is where they are all connected. Okay? So that right there is our triple point. So I will try to look up a video for you guys to show you something like water, I think it is, existing at all three phases at once. But you have to have like a controlled environment, and you have to have like the pressure. You need a machine to make the pressure the right pressure, and then you need to also be controlling the temperature in there in order to get it there. So I've never actually done it before, but that's what we need to know. We are now finished with the chapter 13 notes. Thank you.